Hello everyone, welcome to a new video. And in this video, I am going to explain on how MEMS means what? MEMS is microelectromechanical systems. If some of you don't know that, and how can you use MEMS as a energy harvester or an ultrasonic transducer? Is what I will be trying to explain. Like it will be a very brief, like what you say, a very brief discussion on that of using MEMS as energy harvester and transducer. So let's go to that. So first, I'll do like piezo MEMS as energy harvester. That is the first thing. So what is piezo means? Piezo actually means that you're using a strain and converting it into energy, or you're using a vibration and converting it into energy. The opposite also can be done. That is, the material is able to generate electricity by a strain. In the converse also, like with the electricity you can produce a strain in the material. So I'm not going into details of those things. Yeah, I'm just going to discuss how MEMS is used as an energy harvester or piezoelectric MEMS. Here's actually piezoelectric MEMS. So here what happens is our environment has a lot of vibrations, like right, like we are having vibration in our home by different appliances. You will have vibration in like when a train goes, there is a vibration due to on the rails because of the train. And so these vibration energy is converted to electrical power. So that is that is the main idea of this using this to be used as energy harvester. Okay, so how does it do that? So that is done by the use of two kinds of structures. Maybe even other structures also can do it, but I'll be mainly by explaining two main structures, or these two structures. Like one is a bimorph structure and one is a unimorph structure. So what is a bimorph structure? Bimorph structure means that you have piezoelectric material. I already said like what is a piezoelectric material. Like that's a very brief introduction of that. Like what is happening there. And so here what happens is you have a two piezoelectric material. You have a top electrode you have a bottom electrode is there. And see this blue or these three blue you're seeing are the electrodes, and you have a piezoelectric material, like you have two piezoelectric materials sandwiched between two electrodes. So here and in a bimorph structure, in a unimorph structure, what happens is you have a single piezoelectric material sandwiched between two electrodes, and you have a proof mass. So what is the use of the proof now is that you're actually like the frequency is equal to 1 by 2 pi root of k by m, right? So in that, that as the mass increases, the frequency decreases. So when you're using these MEM structures are at the micro scale, right? So when you're using the structures in the micro scale, what happens is the frequency of the structures will be pretty high. So to reduce the frequency, that is, so frequency is inversely proportional to mass. So you put a proof mass. So by increasing the mass, you are reducing the frequency to lower level. Like the frequency available in the environment is actually the lower frequency, like you can say kilohertz or even the hertz range. So, so if you want to capture those frequencies and then convert in electricity, you need your device to be able to capture. So your device frequency, your device natural frequency should be in that range. So that is why we are putting a proof mass in the structure. So how does it convert? So the basic idea is, so when you have a vibration, the vibration is taken by this structure, either a unimorph or a bimorph structure. Okay, both of them have the same thing. And what happens is this vibration causes a strain in the material, right? And because of this strain, because of the strain, you will ultimately have a charge separation. That is a polarization. In depth, you can, if you want, you can read about it, or if anybody else it out, I can even make a video on like how that is happening. But ultimately, the basic idea, the strain is now converted into separated into charges, and this charge is collected by the electrodes. And ultimately, what happens is due to strain, you are converting the strain into electricity. So that is how it is done. And to extract maximum power, so two things, your vibration should match. So ultimately your structure, this structure is has a resonant frequency, right? So for example, like if the vibration is actually giving you a length extension or width extension, or whatever. Like mostly this will be like a, so it will be a cantilever motion. Okay, so this is a cantilever structure actually. So it will be moving up and down from one end. Okay, one end is fixed. Okay, so that will cause a strain, and that strain is converted into. So ultimately, that structure has a resonant frequency, right? So your vibration or your external vibration should match that resonant frequency, or you should make your structure in such a way that your vibration of the environment matches your structure. And that is one main reason you should consider to extract maximum power. That is one reason. And the second thing you should consider is that you need a wider resonance bandwidth. What do I mean by that? What can I do? Like by a wider resonance bandwidth, I mean that you can put many. So your device. So this is one particular one device, right? So if you want to make, if you can have many devices having different resonant frequencies, then you can exploit all those. You can take in all those resonant frequencies, right? So since the environment has a lot of frequencies, right? It will not come. So idea is to extract maximum power from the environment. You need to build it, build many devices and put it in a stack. Ultimately, you got the idea, right? So ultimately, you are putting many devices, and then for all those resonant frequencies from the environment and catching as much power from the environment and converting it into electricity. So that is the idea. So that is the two main things. To extract maximum powers, your vibration frequency should match the resonant frequency, and you should have a wider resonance bandwidth. Okay. So I'm saying wider resonance bandwidth, like completely device. So you can call this one device, and if you have many such devices in your whole thing, then you can use all those devices to get all the energy ultimately. So what? Considering that you make all the devices with different frequencies, yeah, let's move on. That's the idea. And the main limitation of a energy hours of MEMS is that the electronics consumes more power than generated. So that is the main discussion why this is not till now, like you're not seeing it in the globally like a big thing. Like people are trying to do this, but this is a major thing problem. Is that electronics consumes more power than generated. So still now, people more work is going on, and we hope in future we get a really good energy harvester based on maps. So that's a big challenge which needs to be overcome.
So the next topic or the second topic I'm going to discuss is the ultrasonic transducer. So in this, what happens is, so here it's called a MUT. The MUT means micro machine ultrasonic transducer. So in micro machine ultrasonic transducer, there are two types. One is a CMUT, which is called a capacitive micro machine ultrasonic transducer, and other is a PMUT, which is piezoelectric micro machine ultrasonic transducer. So I would be explaining how a CMUT and a PMUT works here. So here, what is the idea? What is ultrasound transducer? Transducer means you're ultimately converting energy from one form to another. So here, what happens is you are using either using ultrasound and converting in electricity, or the opposite. You can, by using electricity, you can make ultrasound. So that is the idea. So what happens in the CMUT is, so you have a substrate and a top membrane structure. So top, that will be a top, so that will be a top electrode. It can be a metal piece or like whatever thing else. So ultimately, what the idea is, you are a substrate in the top material. So you're applying a DC first between the substrate and the top electrode. So what happens is, and you have a air gap or a vacuum in, I won't say vacuum, you can call it as a air gap in between, or insulation between the top and the bottom. We're applying a uh, DC bias initially. So because of the DC bias, so there's an electrostatic attraction between the top layer, that is given shown in the red here, and in between and the substrate. So because of that, now there's a charge generation, right? And because of the top and the bottom is now attracted, right, a little bit. So on top of the DC, now I'm going to apply an AC. So because of that AC, now what will happen? Already this attracted, and because of your you're made up. with the DC you have produced an ultrasonic attraction, and now on top of that you are applying an AC signal, and that will produce cause the membrane to move up down because of the electrostatic attraction. You understood, right? So that is what is happening. So because of this, what do you call, so ultimately people they call like a capacitance, like you have two layers, like two parallel plates, between them you have nothing. So or you have a dielectric wave, so it's capacitance epsilon zero APD, you know that, right? So that's the base here. That's why it's called capacitor. But so ultimately it's a electrostatic attraction between these two layers, the top, this red one, and this gray one. And when you're applying a AC signal, you're generating ultrasound. So same what happens when you have an ultrasound touching this, and as this membrane starts to vibrate, you will be able to generate an AC signal. That is, from ultrasound you'll be able to generate AC, and from AC if you want you can generate ultrasound also. That is the idea. So the next one is the PMUT. So how in a PMUT works? So here also you have a substrate which is in the gray. Then you will have an oxide layer, that is the green. Then this, on top of that you have a, people use like bottom method platinum, or depends on what you know. This red one is a piezoelectric material. Okay, and the top one you have a top electrode. So what happens in a PMUT is you have a, you apply, so there is a voltage in V in given, right? So you apply a voltage from in the top there, that is, you can call it like an is direction. Ultimately this is is direction, right? So you can think, okay, this is like in the top direction, you can think of an is direction. So when you're applying electric field in that direction, what happens is, so this is the figure of, like, actually PMOT works in two modes. One is a D31 mode and a D33 mode. So this is, you can when you learn more about piezoelectricity, you understand what is the D31 and D33 modes are. These are all piezoelectric constants or piezoelectric coefficients. So what is a D31? So this is actually what, I can just give you a small say. If you give an electric field, you will have electric displacement. So your display electric displacement is will be equal to uh, is a function of electric field, right? So that constant in between, like your your electric displacement is equal to some d constant or a constant, a piezoelectric constant into electric field. So d is equal to d31 d, or like that. So based on that, so so that is the idea. So what is the d31? So like it means that you're applying a, so you are applying a electric field in the three. Three means is the direction. One means x. Two means y. So what happens is, if you are applying a electric field in the three, that is in the z direction, you will have a motion or a strain in the, actually I shouldn't say motion. It's actually a strain in the x direction. So that is the d3 one. So in this figure, or in this PMOT that I've shown here, what that is what is happening. So when you're applying a electric field in this direction, you are getting a strain in the x direction, and because this is actually clamped, you can see this is actually in these two sides it is clamped. So because it is clamped in both these two sides, this compression compression and expansion and compression of this in these two sides causes this thing to, so this is given in an AC signal, right? So that's why you have expansion compression, and because it is fixed, and because of the strain in the x direction causes this fixture in both sides, causes it to start vibrating in the z direction. So that is the idea that is happening. So that is what is happening here. So ultimately, what you're doing in a PMUT, in a PMUT also, you're actually using piezo, that is a piezo material, and then by supplying an electric field in this direction, you're converting it, you're producing a strain in the x direction, and ultimately making, because of its fixed direction, fixed in the both direction, you're able to get a motion in the z direction, and that is how you are able to generate an ultrasound. So space, and opposite, if you get an ultrasound, then you can generate electricity from that. So that is how you are using these two MEM structures to produce ultrasound, or even from ultrasound to produce electricity. So that is the basic idea in this. ultrasound transducer. So I hope so. This is ultimately this is all I have made in this video. So that is the idea. So this is just a brief introduction or a brief idea I've given on how MEMS is used as a ultrasonic transducer or a energy harvester. So that's all in the video. So if you like the video, please do like it and also subscribe to my channel. It will actually motivate me to make more videos. And yeah, thank you.